Good day, Doctor. Today, we are going to present our Mechanics of Materials assignment project. We are from Group 2, and I'm Juan Yi. Our members include Sao Yu, Faris, Shamar, and also Jung Hao. So, let us move to the introduction part first. Our background. The project is to build a cylindrical bar from uncooked spaghetti. After create it, we must test the bar until it breaks. And this test is called a bending test. So we can know the maximum weight the bar can withstand. Then we will use the result to calculate the stress inside the bar before it breaks. It helps us understand how material behave under pressure. We have four objectives. The first one is to create a cylindrical spaghetti bar that is exactly 30 cm long and 1.5 cm thick. So we got a spaghetti that is not exactly 30 cm, so we need to figure out how to do it. Later, my groupmate will explain it to the doctor. So the second one is to test the bar until it breaks. So the third one is to calculate the normal stress at the breaking point. And so also the fourth is to suggest a safe stress limit using a safety factor of 1.5.
Hi everyone, today I will present about the model fabrication method part. There are three highlighted points that we want to show here. The first one is the material selection. We use spaghetti of any brands, a clear tape and a duct tape. And then for the geometry constraints, the spaghetti must be shaped into a circle bar that the diameter must be no more than 1.5 centimeter. The length of the bar must reach 30 centimeter and 2 centimeter on each end, acting as the holding point. Next, we go to the connection and adhesive. The existing spaghetti in the market did not reach the 30 centimeters minimum length. So, the bar was separated into three sections with 10 centimeter length each. The spaghetti on each section was taped by using clear tape to hold the circular shape together. All three sections were then taped together using duct tape to form a 30 centimeter bar. Next, we go to the testing part of the group assignment. There are three highlighted points here: the support, loading mechanism, and measurement tools. For the support, each end hold the bar with 2 centimeter length. The loading mechanism, a single string was used to hang the water bottle attached in the middle of the bar. And then the measurement tools, water volume increased by 100 milliliter at a time using a measuring cup. Next, for the result part of the experiment, we have three parts here: the pre-experiment, experiment, and post-experiment. For the pre-experiment, the spaghetti bar were put in the gap between two tables. An empty bottle will hang in the middle of the bar. During the experiment, 100 milliliter of water load measured using a measuring cup, and then the water will be poured into the water bottle and increases continuously for a while until the spaghetti bar started to bend and split into two. And then while we're doing the experiment, we reached the 3,100 milliliter. After that, the post-experiment, the mass were calculated by using the density of water and its volume. And then the weight were calculated by using mass and the gravitational acceleration. That's all from me.
We can do analysis by sectioning method to determine shear and moment for maximum loss. And second is to suggest the allowable normal stress when the safety factor is equal to 1.5. Third is determine the shear and moment function for the all tested loss calculation. And finally, we can generate the shear force and bending moment diagram. we need to draw the free body diagram for calculation, and the assumption we do is 1 liter water is equal to 1 kilogram water, and the maximum load we get in testing is 3.1 kilogram water, and the force L applied in the middle section of spaghetti is equal to the 3.1 kilogram times gravity, and finally we can get 30.4 newtons. And then we need to find the reacting force at point A and the point D. For for the first equation we use is the sum of moment equation at point A is equal to 0, and we can get Fd is equal to 15.2 newtons. And second is the force in y-axis is equal to 0, and we can get force at point A is equal to 15.2. After we get the reacting force at the point A and the point D, and the force applied by the maximum loss in the middle section of the spaghetti, we can divide the spaghetti into four sections and do the summation of Fy equal to 0 and summation of moment equal to 0 for each section. And finally, we can get the conclusion is the first one is the bending moment is 0 at both supports. And the second is the magnitude of shell over sand. The third is the maximum moment is equal to m2 and m3, which is 2.13 Newton meter. We need to suggest the allowable stress when the safety factor is equal to 1.5. In this part calculation, we will involve the two equation, which is the safety factor is equal to ultimate stress divided by the allowable stress. And the second is the ultimate stress is equal to moment times y bar divided by the inertia of moment. In step 1, we need to find the ultimate stress first, and the maximum moment we get in previous is equal to 2.13 Newton meter, and the maximum y bar is equal to radius of the circle, and the inertia of moment is equal to 1 over 4 pi times r power of 4. And finally, we can get the ultimate stress is equal to 6.43 megapascal. In the step 2, we need to find the allowable stress. The allowable stress is equal to ultimate stress divided by the safety factor. And finally, we can get the allowable stress is equal to 4.3 megapascal. To calculate the all tester loss, we can determine the shell and moment function firstly. And we can assume the load applied in the middle of spaghetti is equal to 2F. And the range of 2F actually are all the tester loss. And we can do the overall summation of moment at point A and the summation of force at y-axis is equal to 0, and we can get the reacting force applied at the point A and the point D is F. Okay. From the conclusion in previous part, we get the magnitude of shear over sand and the maximum moment present at the second and third section. We can consider the second section as our basis of calculation, and we use the summation of Fy is equal to 0, and we can get the shear is equal to F. And the second is we use the summation of moment is equal to 0, and we can get the maximum moment is equal to 0.14 F. Since the radius and inertia of moment of the circle is remain, so we can use elastic section modulus to express its relationship. So in this case, we can use ultimate stress equation is equal to m over the constant s, then is equal to 3.02 times moment. Let us to see an example is when the 0.6 liter of water is added, there are 0.6 kilogram of water. So the 2F is equal to 5.89 and the F is equal to 1 of half of 2F is equal to 2.94 and the shear is equal to F and is equal to 2.94 and the moment is equal to 0.14 times F and is equal to 0.41 and the ultimate stress is equal to 3.02 times moment, so it is equal to 1.24. Okay.
And now I will introduce our shear force and bending moment diagram. The first diagram is our FBD of our beam, and this is a simply supported beam of 0.3 meter, 30.4 newtons locked at the middle of the beam, creating symmetrical upwards reaction of 15.2 newton at both support at 0.01 meter both ends. The second one is our shear force versus the length of the beam. The shear force set at positive 50.2 newton at initial, 30.4 newtons drop suddenly at the center, and remains at negative 50.2 newton at final. The last diagram is our bending moment versus the length of the beam. The moment changed linearly, starting from the zero at both ends and peaking at the middle of the beam, with a maximum value of 2.13 Newton meter.
So, to conclude our project, we have successfully built a spaghetti bar that was 30 cm long and had a 1.5 cm diameter by using the help of paper mold and tape. Our spaghetti bar broke when it reached a bending moment of 2.13 Newton meter, which correspond to 3.1 liter of water we added during the test. By using the data we got from the test, we have calculated the ultimate stress to be 6.43 megapascal, and by using a safety factor of 1.5, the safe allowable stress is turns out to be 4.3 megapascal. So our final thoughts on the project is our spaghetti bar was surprisingly strong, but it broke suddenly after the maximum volume of water is added. So this experiment shows us how important it is for us to understand the limits of material before we use it in our real life. Lastly, there are a few things that we have learned throughout the project. First thing, we learned about teamwork because we had to do work together to solve the problem of short spaghetti. We have to discuss with each other on how we want to combine the spaghetti and which length of each segment of the spaghetti is more suitable to make sure our spaghetti bar can hold a maximum load. Next, problem solving. We need to use our creativity to solve the problem of thickness by using a paper mold to help us shape our spaghetti bar. Next, we also need to use practical application because we need to use the formulas and the math that we learned from our mechanics of material class to help us to calculate the ultimate stress and also the safe allowable stress. Last but not least, we also need to do a careful testing by using 100 ml increment to allow us to get an accurate breaking point of the spaghetti bar. That's all from us. Thank you.